Good day, viewers. You are welcome back to Tindanious Math and Science tutorials. You are very welcome to this channel. We are still treating complex numbers. In fact, we've done a lot. So in view of that, I've created a playlist where you can access all my videos pertaining to the topic complex numbers. So if you are new here, kindly subscribe, like, share and comment for more interesting videos and updates. Additionally, I have created a playlist on calculus, differentiation and what have you. I've done a lot. So if you are watching me now and you think you want to be very good at differential calculus, visit my playlist on calculus, as well as functions, transformations of functions. Everything is well explained. So kindly hit up the subscription button. So today we are going to talk about de Moivre's theorem. It's a name of a scientist, okay? So what is the concept behind de Moivre's theorem? Now, you will be given a complex number either in the rectangular form or the Cartesian form. You can also be given the complex number in the polar form or the circular form as well. And this complex number will be raised to a certain power or exponent. And when this power approaches a very huge or a large value, it becomes very cumbersome to deal with it. So de Moivre's theorem is just there to simplify these complex numbers for us. So this is the whole concept behind de Moivre's theorem. So when you have large exponents or powers, de Moivre's theorem will have to be employed in order to what? To simplify or ease calculation. Also, de Moivre's theorem is used to simplify trigonometry identities or questions under trigonometry functions. De Moivre's theorem also plays a significant role. I will also prove de Moivre's theorem using the principle of mathematical induction. I decided not to prove it using mathematical induction because I'll create a playlist pertaining to mathematical induction. I will also incorporate de Moivre's theorem as part of the topic. So when you have this square root of 3, then plus I, then square root of, let's say, 3 raised to the power 2 this way. This is very easy, okay? You can just do this very easy. You can decide not to employ de Moivre's theorem. But what if you have questions like this, plus I, then 3 raised to the power 100? Oh, viewers, how would you be able to do this? To the 100th power. That would be very what? Difficult to do it. Okay? In order to solve this question, you will really suffer. As a result of that, we need to employ de Moivre's theorem. So de Moivre's theorem is simply used to find for what? For powers of complex numbers, and it is also used to find for roots of complex numbers. So to appreciate this topic very well, let's solve some calculations to throw more light on de Moivre's theorem. So let's work out to the first question. Evaluate, okay, or find 1/2 plus I and 1/2 this way raised to the power 5. Let's solve for this. Okay, remember this is in the rectangular form, right? You can change this to the polar form. So we want r and theta, okay? So my r, which is my modulus, square root of 1 over 2 all squared plus the imaginary part all squared 1 over 2 all squared. Half r is equal to, so this gives 1 over 4 plus 1 over 4, and this is equal to, we have 2 over 4, which is equal to 2 divide itself 1, divides here 2, so I have 1 over 2, which is equal to square root of 1 is 1 over, then we have this way. So this is my modulus. You can decide to rationalize. You still get the same answer. So we've gotten r to be 1 on root 2. Let's look for our argument, okay? So our argument, we have theta, which is equal to tan inverse of y over x, not x over y. So we assume this is my y and this is my x, right? So I have theta is equal to tan inverse of, I have 1 on 2 over 1 on 2. 2 cancels 2, right? So I have theta is equal to tan inverse of 1, which is equal to, I think, 45 degrees. You can convert this to radian, okay? Or you can say, oh, that's 1 over 4 pi radian. So this is my argument, right? Now, because we are working in the first quadrant, positive, positive. I have positive x-axis, I have positive imaginary axis. So the angle theta is equal to the angle alpha. So I don't need to make any modification. So this is clearly what we are looking for, this and that. Now, the Moivre's theorem states that when you have z this way raised to the power n, okay, let me state the theorem clearly over here. Now, the Moivre's theorem is saying that when you have complex number in the polar form this way, r, then I have cos theta plus I sine then theta this way. Now, when I raise this complex number to a certain power, so let n denote what? The power, okay? So if I have it this way, like this, raising the whole of this to a certain power n, what you do to the left hand side, you do the same to the right hand side. I'll raise this to what? To a power of what? Of n. So this becomes z what? N, which is equal to. Now, the Moivre's theorem is saying that to raise a complex number to a certain power, which is n, you will raise the modulus to n, okay, to an exponent of n, and that n or that power multiplies the argument. That is simply the Moivre's theorem. So this n multiplies the modulus, which is r to the power n. Then this multiplies, we have cos of, we have the angle theta, which is the argument. So the argument multiplies the power. So we have n, then theta, then plus I sine, then we have n theta, right? N theta. Okay. This is the Moivre's. But the question, we have this. Is that also? So I can say this, my n is my 5. That denotes the power, that's the power. So n is equal to what? 5. And my r is 1 over what? Root 2. So I have 1 over root 2 this way, right? And my angle theta is equal to, permit me to work in degrees, okay? 45 what? Degrees. So I have z raised to an exponent of n. N is what? 5. So I have 5 is equal to 1 over square root of 2, right? Raised to an exponent of n, which is 5. That is 5 multiplying, I have cos n by theta, right? So I have 5 times this, which is this. Is that also? Then plus n is 5 times 45 this way. So I have z to the power 5 equals 1 to the power 5 over this to the power 5. Remember the law of indices, so I have a over b to the power x. This is the same as a to the power x over b to the power what? X, right? So in this we have cos. So 5 by 45, we have 2 to 5, okay, degrees, then plus I and sine, then 2 to 5 degrees. And this is the same as z to the power 5 is equal to 1 over, then this becomes 4 root 2. Multiplying, I have cos 225 degrees plus I sine 225 degrees. Viewers, this is the end of this question. So I will give you the same question raised to an exponent of 10, and let's see what happens from here. Viewers, we have the same question, but this time around raised to an exponent of 10, right? You just follow the same formality. Find for your modulus r. Find for your modulus r this way, and your argument this way. You arrive at the same answer, which is 45 degrees. Now, let's employ this using the Moivre's theorem. And we already know this, right? We know this. Now, what is our exponent now? It's 10, not 5 again. So we have 10. Our r is this, and our argument theta is also that. So when we apply the Moivre's theorem here, to be the modulus raised to that power, which is what? Which is 10. Then this power 10 multiplies the angle given in question. That's the angle we found for. Alright? So we have 10 times 45. We have 10 times the angle 45, right? So this is the same as 1 to the power 10, right? Over then square root of 2 to the power what? 10. This way. So we have cos of 10 times 45 this what? 450 degrees. Then 10 by this also is for 450 degrees, right? So now I have the whole of the, when you compute this, you get 1 over 32, yeah. Multiplying 450 degrees plus I sine 450 degrees. So this is to the power 10, to the power 10, and to the power 10. This is the final answer. You can decide to multiply this by this, then this by that, to convert your answer to the rectangular form. So if you do that, we are converting this to the rectangular form. Yeah. So we have it this way. To convert this to the rectangular form, you have 1 over 32. This multiplies this, right? Times cos 450 degrees. Then plus 1 on 32 times I sine 450 degrees. This is 1 on 32, then times cos 450 gives 0, then plus 1 on 32 times I have my I times sine 450 gives 1. So clearly this becomes z to the power 10 is equal to, the whole of this goes to 0. Then plus this is, I think I over 1 times I is I times 1. We have I, we have over 32. So therefore, you can say z to the power 10 is equal to 1/3 plus 1/32, then r. Viewers, this is the end of the question. Have you seen the importance of the Moivre's theorem? To simplify calculation, we use it to find powers of complex numbers. We use it to find for the roots of complex numbers. So we will end this video session, okay? So when I meet you next time, I'll still solve example to throw more light on the Moivre's theorem. Bye.